going to go over this problem from the notes. If you want to make a clean copy, which I recommend, you can go to my website and go back to class, I don't know, 3 of this semester, open up the PDF right here, or it's probably in here again, it's just Unit 5 handout. So click that, print out page 8, or just look at page 8. But don't look at the answers while you do it. Maybe watch this video, then go back with the blank copy and do this. So here's what I recommend. First, if you're doing this, let's just cross out these 3 columns. They're not going to be on the test. They're considering all types of energy to get total energy, which never changes. That's always conserved in a closed system, which we're considering this to be. Mechanical energy can change, though. And that's actually where I'm going to start. So I think what you should do is read the problem, look at what's going on, get the lay of the land, and then figure out where total mechanical energy is changing. So get your formulas. Top ones are for circular motion, so I'll just fold this over. We don't need those. This is the main one right here. This is just saying total mechanical energy, which is the sum of potential energy and kinetic, is going to be the same. So this total equals that total, unless there's some work. And the work is either positive or negative. Positive work adds energy to the system, negative work takes it away. And I'll tell you, in this problem, on the retake, you can expect a few things. You can expect one place where energy is added to the system. You can expect one place where energy is taken away from the system. I mean mechanical energy. So one place where there's positive work, it's going to add to this total and make this total bigger. One place where there's negative work, which is going to make the total smaller. And when I say place, I mean a transition between these locations, either between A and B, or B and C, or C and D, D and E. And what I would do first is figure out where those places are and make a little note over here in the mechanical energy column, because it's always going to be the same as long as there's no positive or negative work done. I'm not going to read all this, but if you do read all this, you'll read at some point that the electric motor here is doing some work. It's exerting a force on the car over a distance. And that's giving it a push in the direction it's going. That's not slowing it down, that's helping it up this hill. So I have identified the place where there's positive work between A and B. So I'm going to make a little note right here. I'll circle both of these, and I'm going to write mechanical energy increases. So between A and B, there's going to be an increase of mechanical energy. And if you read the problem, it says there's no friction, there's no drag, there's no nothing except right here where the brakes are applied. So the brakes are going to be the negative work. So between D and E, between these 2 boxes, mechanical energy decreases. The amount that it decreases by and the amount that this increases by is equal to the work done by something. And work is force times distance. So in this case, right here, the thing doing the work is this electric motor. And here you're given the force, and there you're given the distance. Here, the thing that's doing the work is friction from the brakes. You're given the force, and again, you're given the distance. So this is going to be negative work, this is going to be positive work, and here you can calculate each of these just by multiplying force times distance, but make this one negative so that the total energy decreases. Aside from that, so between B and C, this is the same as this, and from E to F, the mechanical energy is the same. So it only changes from here to here and from there to there. Everywhere else, mechanical energy stays the same. If you keep that in mind, and you know that the change here, the amount that this increases or decreases, is the work done in these 2 places, then all you really need other than that is these other formulas for calculating the various types of energy, and maybe this formula for calculating work. But I've got my answer key off to the side. Better not to look at that. I'll just show you the order in which you could figure some of this stuff out. So I would recommend doing the low-hanging fruit, which is to just calculate some of these energies. We've got 3 different types of mechanical energy. This one, and this one. And those 3 types together add up to that. That's useful knowledge. You'll need to use that bit of knowledge later on. But if you have everything you need, you can just calculate these. So gravitational potential energy is mgh, which means, since I know the mass of this thing is 200 kilograms, and I know g is 9.8 meters per second squared, whenever I have h, which I have right there, I can calculate gravitational potential energy. So 200 times 90 times 9.8 gives me 176,400. The spring potential, there's going to be a spring in here, and the only time there's any spring potential energy is when the spring is compressed. So the card is here. It doesn't compress the spring until it gets over there. So whenever the spring is not compressed, there's none of this. So I guess I'll just go ahead and put in 0, 0, 0, all the way to position F. And maybe I can calculate that if I have the information I need. But with gravitational energy, that's the only one I have the height for. So that's all I can do right now. Kinetic energy, more low-hanging fruit, 1/2 mv squared. So wherever I have the mass, and wherever I have the velocity, I can calculate kinetic energy. So that gives me a lot. The kinetic energy here is 0, because v is 0. And there it's 0, because v is 0. And there it's 0. And here, 1/2 mv squared comes out to about 68,600, if my answer key is right. All right. And while I'm at it, let's see if I can do a spring potential. This is the formula for spring potential energy, and I said there is potential energy there. It's 1/2 kx squared. K is just the spring constant, and we're given that, 1560 newtons per meter. That means for every meter this is compressed, you have to apply 1,560 newtons of force. X is the compression distance, and we're given that, so we can calculate this number right here. It's 1/2 times k times x squared, so 10 squared, and that comes out to 78,000. And that's all the low-hanging fruit. I've used these 3 formulas to calculate everything in these columns that I could, and that's all I can do. Now I've got to use the fact that there are 2 things I'm going to be using. I know how much these are going to increase or decrease by, and I can also find total mechanical energy by adding these things up. What I'm going to be able to do too is, once I have mechanical energy, I'm going to be able to infer or deduce what some of these other things are inside here. Let's see. Okay, so I think what I'm going to do, I'm going to find out how much this increases by, and I'll find out how much this decreases by. Actually, I'll wait. I'll do that next. What I want to do is add all these up if I can. There's only one place where I have all 3 types of energy, and it's right here. So this is 176,000 joules of potential energy right there, no spring energy, no kinetic energy. The total is 176,400 joules of energy. That's the only place I can add all 3 of these up, unless I'm missing something. So now I'm going to do what I was going to do a second ago. I'm going to figure out how much mechanical energy increased by, and that equals the work done. And specifically here, it's the work done by this motor. So the work done by the motor is the force, 1,120, times the distance over which the motor is applying the force, 70 meters. And that comes out to, well, you know what? On my answer key, I don't think I really showed that. So let me do that now. 70 times 1,120 equals 78,400. So that's the work that was done there, and that's how much the energy increases, the total mechanical energy increases from here to here. So if I could write a little equation here if I wanted to, I could say like ME0 plus 78,400 equals ME final, which is 176,400. Or I could just say, I'll take 176,400, subtract the work that was just added to it. Oh, well, anyway, it was 98,000. So 176,000 minus that 78,000 joules, which is the amount that this increased by, gave me 98,000. Now that I have that, I've got zero kinetic energy, zero potential energy, or spring potential energy. These three have to add up to this, so all of this has to be gravitational. Now I can use the gravitational formula. Since I have this has to equal mgh, and so I just solve for h, which turns out to be 50 meters. This 176,400 stays the same here because there's no work done between B and C. There's no friction or anything. Like I was saying earlier, this stays the same except when there's positive work here, which means it's bumped up, or when there's negative work, which means it's bumped down. Let's see. Oh, so there was a little bit more low-hanging fruit earlier. I'm given this height 30 meters, this height 90 meters. This isn't really height, but this is the difference. So that means the height at C is 60 meters. And I can do MGH. H, M, G gives me, let's see, 117,600 joules of gravitational potential energy. And since I know the total is 176,400 and I know there's no spring, then this plus this kinetic energy should add up to that. I can just do 176,400 minus 117,600, and that is 58,800, I think. All right. Between C and D, the total mechanical energy stays the same, so that's still going to be 176,400. It's going to decrease, though, between D and E because of these breaks. But since I know this is 176,400, and I've already calculated the kinetic energy here, and there's no spring potential, this must have to make up the difference between this and this, because these three have to add up to that. So 176,400 minus 68,600 tells me how much of the energy is still gravitational, and that turns out to be 107.8. Now, one thing I can do, since D and E are at the same height, I can calculate the height now. Since I have this is MGH, so set MGH equal to this, plug in the mass of 200, plug in G, and you can find H, which is 55 meters. I know that E is at the same height as D, so that's also 55 meters, and the gravitational potential energy is going to be the same. The total mechanical energy, though, has got to decrease, and it decreases by the amount of work that's done here, which is the force of the brakes, 500 newtons, times 40 meters, and I'm going to put a negative there, and that ends up being negative 20,000. So by the work, by brakes, negative 20,000 joules. So if this is 176,400, the brakes do negative 20,000 joules of work. This is now 156,400. And that's the total mechanical energy, so all these have to add up to the total, which means this has to be total minus that, which is 48,600. Now that I have kinetic energy, which is 1/2 mv squared, that allows me to set 1/2 mv squared equal to this, plug in the mass of 200, solve for v, and v comes out to about 22 meters per second. And then finally, between E and F, there's no friction, no nothing, so the total mechanical energy doesn't change. The kinetic energy is 0 because it's not moving. The spring potential energy is now this because the spring is compressed that much. So if the total mechanical energy is this, these three have to add up to that, which means the missing one, gravitational, is the total minus 78,000, which is 78,400. And once we have that, we can set that equal to mgh, plug in the mass of 200, plug in 9.8, solve for h, and h turns out to be 40 meters. So to sum up, first step, read the problem, figure out where the total mechanical energy is changing. Changes between here and here as something adds energy to the system. And then it decreases from here to here as the brakes take energy out. On the retake, there's going to be some friction removing mechanical energy. There's going to be something else adding mechanical energy. Each is just going to happen once. So aside from that, the total stays the same, like from here to here and here to here, and then finally from there to there. Beyond that, whenever you have information that will allow you to just plug stuff into mgh or 1/2 kx squared or 1/2 mv squared, you can calculate these. When you can't calculate them, you may need to use the knowledge that the three of them add up to the total. So you'll be able to potentially figure out one of these if you know the other two. And then for velocity, if you're not given velocity, you can always calculate it when you know kinetic energy. In this case, 58,800 equals 1/2 times 200 times v squared. V has to be 24.2. And you can calculate height when you know potential energy. And also, if two things are equally high, like they're straight across, you can assume they're at the same height. So if you find one height, you found the other. Guess that's it. I don't know what else I can say. So print yourself a blank copy. Try to do it all by yourself. Think through what you're doing. If you don't know why you're doing what you're doing,